Hi everyone, today I'm going to go over Lab 4. Today's lab's topics will be on fractions, fixed point, and IEEE. To begin, let's review some key concepts. In IEEE, we have two different systems: single precision, which consists of 32 bits, and double precision, which consists of 64 bits. Today, we will mainly be working with single precision. As a reminder, we have one sign bit allocated in the front, 8 bits for the biased exponent, and then 23 bits for the mantissa. In our double precision, since we have more bits to express our biased exponent and our mantissa bits. The number of bits we assign to the sign is the same, which is 1. One interesting thing with IEEE is we have this biased exponent. Our biased exponent is what we get from adding our actual exponent to our bias. Over here, you'll see that if we have this IEEE binary number, we can get the biased exponent from those 8 bits following the sign bit. In single precision, we have 8 bits allocated for the biased exponent. But in single precision, we can use this formula to calculate our bias. This K represents the number of bits for exponent. To calculate our bias, we'll do 2 to the 8 because in single precision, we have 8 bits for our biased exponent. So we'll do 8 minus 1 minus 1. This will be 2 to the 7 minus 1, which is equal to 128 minus 1. So our bias will be 127. Every single time you're in single precision, you will be using 127 as your bias. Once you have your bias, you can look at your IEEE number to calculate your biased exponent. When you subtract your bias from your biased exponent, you'll get your actual exponent. You can use your actual exponent when we're working in binary normalized form. Over here, we have S representing the sign bit, M is representing our mantissa, and then E minus B is our biased exponent minus our bias, which is E, our actual exponent. All of these formulas will be useful for working on today's lab worksheet. Alright, we're going to go over question 1, where we are asked to convert 3.875 to binary. Our first step is to convert the whole number. 3 to binary is 0b0011 or 0b1. Then we want to convert the decimal, or the fractional part. If we have 0.875, the way that we will convert it to binary is instead of dividing by 2, we will actually multiply by 2. 875 times 2 is 1.75. Over here, we'll use the 1 to keep track of our final binary number, and then we'll use the 0.75 as our remainder that we could use to multiply for the next line. And we're going to keep going until we've done this 4 times or until we've gotten 1.0 on the right side. So 0.75 times 2 is equal to 1.5. We'll take that 5 as remainder, and then 0.5 times 2 equals 1.0. Okay, great. Now we have our binary. We're going to go down for our most significant bit and to our least significant bit when we're getting the fractional part. So our final answer will be 0b11 for our whole number, dot decimal, and then since we're going from the most significant bit to the least significant bit, our fractional part will be 111. So our final answer is 0b11.111. And that is how you convert a decimal number to binary. In prompt 4, we are asked 3 different questions. To begin, we're asked to use a 16-bit 8 plus 8 fixed point system with 2's complement encoding for the whole number portion. This means for our final answer, we'll have 8 bits allocated to the whole number, which will be in 2's complement, and then 8 bits for the fractional portion. Our first question asks us, as a decimal mixed fraction and also in binary, what is the value of the number closest to 0? As a reminder, we are in a 16-bit 8 plus 8 fixed point system. To begin, let's look at the number line. Over here, we have our positive numbers on the left and then our negative numbers on the right. The closest value to 0 would be the smallest positive fractional value. An easy way to solve this is if we look at our final answer, we'll have 8 bits for the whole number side and then 8 bits for the fractional side. To get the smallest fractional value, we can totally ignore the whole number part and then go over to our fractional part and look at what is the smallest value we can make with our fractional bit. And the answer to that would be having 1 bit turned on at the very last bit for the fractional part. This represents 0 times 1/2 plus 0 times 1/4. Again, these are representing 2 to the 1, -1, 2 to the -2, and so on until we get to 1 times 1 over 2 to the 8th, which is equal to 1 over 256. So that would be our smallest fractional value that's positive. So in binary, this would just look like 0b. And that would be the value of the number closest to 0. The next question asks us, what is the value of the furthest negative from 0? In this case, we'll be looking at the right side of the number line, and the furthest negatives from 0 is essentially the smallest number, or the greatest negative. And by great, in this context, we mean furthest from 0. To find the value of the number furthest from the value of the furthest negative from 0, let's start with our 8 bits. If we have 8 bits over here for our whole number, and we are in 2's complement, we know that if we just turn on the bit to the furthest left, that will give us the greatest magnitude, and since we are in 2's complement, that first bit being 1 signifies that it is also negative. So now we have our greatest negative whole number. This is equivalent to -1 times 2 to the 8th, or actually, sorry, 2 to the 7th. And then over here, since we want our fractional value to be as great as possible, so it's further away from 0, we'll just fill it in with all 1s. So this will be equivalent to -128 and 255 over 256. This is the decimal value. So our final answer is 0b 100000.11111111. So this is where 0b Finally, we are asked to convert the following number to binary in 16 bits. We have a mixed fraction, which is 1981 over 32. Our first step is to convert the numerator Alright, so this is our 1981. We just converted it to binary. Now, how should we go about getting it into its fractional form? Well, one thing you'll notice is that 1981 has 32 on the denominator. Because we have 32 in the denominator, 32 is a power of 2, since 32 is equivalent to 2 to the 5. Because of that, we can actually apply a very quick trick. Since 32 is equivalent to 2 to the 5th, we can move our decimal point left 5 times. 1, 2, 3, 4, 5. Each time we move our decimal point to the left, we are actually dividing our number by 2. So then our final answer becomes 111101.11101. In this case, what we did is we just multiplied our value by 1 over 2 to the 5 by shifting right 5 times. So now our final value will be 0b 111101.11101. For this question, we're asked to convert this number to IEEE form. We have the number 0x C14C0000. In this case, our first step should be to convert the number to binary and then answer the remaining questions. By now, you should be able to convert hex to binary fairly easily. Now that we have our binary number, we can get to identifying our sign bit, our exponent, our biased exponent, and then our mantissa. One thing you'll notice is that we are working in single precision. This number is 32 bits. Since we have 8 hex digits, 1 digit is equal to 4 bits. So we have 8 times 4 equals 32 bits, which is the same as in single precision. We know that our first bit is reserved for our sign bit, the next 8 bits will be for our exponent, and then the remainder are for our mantissa. Our first question asks us, is a number positive or negative? Well, we know our sign bit is 1, which indicates that our number is negative. The next question asks, how many bits will a single precision biased exponent consume? What is the actual exponent in decimal? Well, we know in single precision, our biased exponent will consume 8 bits. We know this because of this little indicator that we had used earlier, 8 biased exponent bits. Now let's calculate the actual exponent in decimal. First, we have our biased exponent, which we need to calculate and convert to decimal. We just calculated our biased exponent and we got 130. We know that our bias in the 8-bit system, minus 1 is going to be 127. So to get our actual exponent, which is E equals E minus B, we do 130 minus 127, which gets us 3. So that will be our actual exponent. The next question asks, what is IEEE 754 number in binary normalized form? As a reminder, this is our binary normalized form notation. We have our -1 to the power of our sign bit, 1 point our mantissa, times 2 to our actual exponent. We know our sign bit is 1, so -1 to the 1 will be the first part. Then we have 1 point, and then let's look for our mantissa. Our mantissa is 1.0011, and then the remainder are zeros. So we can just do 10011. Then for our last part, we're multiplying by 2 to our actual exponent, which we got over here. So it'll be 2 to the 3. And that will be our number in binary or normalized format. Now let's get the mantissa in hexadecimal. This is the mantissa that we had found earlier. Notice that we don't actually have an even multiple of 4. We only have 23 bits for a mantissa, but we can pad with a 0 in the front when we isolate our mantissa and we're converting it to hexadecimal. However, if you're looking at the normalized format, you cannot pad with a 0 in the front. So in this case, let's convert this number to hexadecimal. I just realized that I had miswritten the mantissa in the beginning. The mantissa should have 8 more bits of zeros. Correct our mantissa. We should actually have 2 extra 0 digits. So our final value will be 0x4c. 0000. Our final question asks us, what is the number in base 10? We can use our binary normalized form in order to calculate this. First, we know that because we have our sign bit as 1 here, negative 1 to the 1 will be negative 1. So our final answer will be negative. We have this binary number over here that we need to convert to decimal. But first, we need to multiply by 2 to the third. So if we multiply by 2 to the third, what we're doing is we're going to shift this decimal point 3 times to the right. So we get 1100.11. This in binary and decimal is equivalent to 1 times 2 third plus 1 times 2 to the second plus, and then in our fraction form, we have 1 times 1 over 2 to the 1 plus 1 times 1 over 2 to the second. This will become 8 plus 4 plus 0.5 plus 0.25. And then our final answer will be negative 12.75. And that is the decimal form of our number. Thank you for watching, and I hope this video was helpful.